So let's learn how to solve a system of first-order differential equations where the eigenvalues and eigenvectors of the matrix A are complex conjugates. So here's our system, x prime equals ax, where the eigenvalues of A are lambda equals alpha plus or minus beta I, and the eigenvectors are given by the vector v equals the vector A plus or minus the vector bi. So we know that if we have the eigenvalue alpha plus beta I and the corresponding eigenvector A plus bi, then our solution is given by x equals v times e to the lambda t. So we're going to replace the vector v with a plus bi, lambda with alpha plus beta I. And you remember when we were solving second order equations with complex conjugate roots to the characteristic equation, we used Euler's formula, e to the I theta equals cosine theta plus I sine theta. So here we just simplify e to the alpha plus beta I times t. We rewrite that as e to the alpha t times e to the I times beta t. And here we replace, this is our theta for using Euler's formula. So we rewrite this expression as cosine beta t plus I times the sine of beta t. At this point, we just factor out the e to the alpha t. We take the vector A and multiply by cosine beta t. The other real part we'll get when we multiply b I times sine beta t. I times I is I squared, and we know that I squared is -1. So we get a minus b sine beta t from this product. And then for the imaginary parts, we get b times cosine, and we get a times sine. And so then we get this expression. So here, the first part is the real part. The second part here is the imaginary part. And we'll write those down. So here's the real part, and this is the imaginary part of the solution that we just found. Now, the solution we found is x equals x of 1, the real part, plus I times the imaginary part. Now, if you differentiate this, you get this expression. You're just differentiating each component. And when we substitute into x prime equals ax, and we know x is a solution, we get this expression. This is x prime, and this is a times x. But when we multiply a matrix times this expression, we can just multiply that matrix A times x of 1 plus I times A times x of 1. And that's what we get here. Remember, x is a solution. So the real parts, the things I've underlined here, the real parts have to equal, and the imaginary parts have to equal. So that tells me x of 1 prime equals a times x of 1, and x of 2 prime equals a times x of 2. This means x of 1 is a solution. This means x of 2 is a solution to the system. So what does this mean? That means that x of 1 and x of 2 are our two linearly independent solutions of the system. We didn't prove that they're linearly independent, but they are. So whenever you have a complex conjugate, eigenvalues and eigenvectors, when solving a system, you just use these two formulas for your two solutions. And we'll solve an example next time.